Okay, I'll just continue. So I wasn't completely sure what the first speaker was going to say. So that sounds like a joke, but it's actually more true than you would think. But anyway, it doesn't hurt to re-show this. So this is the experiment that motivated these studies. And again, just to emphasize a few points. This image is a photograph from above, streamwise direction, spanwise direction. Again, the emphasis here is on very large length scales. If you were to look at this experiment edge on, you would basically be seeing that blue line. That's the fluid you'd be seeing between the plates at this aspect ratio, as close as I could get it. Again, the length scale that Lorette mentioned that we'll mostly see here is something like 40 if you view this as a pattern formation problem. It doesn't hurt to emphasize that in the streamwise direction, this is a length scale of about 100 in these units. And that's over 2,000 in wall units, just to give you some, I'm not a wall unit person, but I just thought, I know a lot of people here are, and they like to think in those numbers. Okay, so I will make some comments that the emphasis here is a little bit different. So, so we have this this is just a schematic picture. There's a laminar Couette solution that exists and is linearly stable at all Reynolds numbers. This kind of sketch has been produced several times here. There's turbulent flow up here, different branch beyond some Reynolds number. There's a boundary here which may be quite complicated. I just want to emphasize, I'm not looking at this issue we're not looking at this transition issue. We're not trying to perturb and go up here. We're staying up here. We're actually trying to go as high as possible, or as high as we need to get something that's everywhere turbulent. And then we're scanning down, maybe going back up and scanning down, but we're trying to avoid any issues with regard to this. Let me just emphasize, and Paul brought this up yesterday, I'm very much in agreement. Size does matter in these things. Obviously, these appear only on very large length scales. You need large length scales to see them at all. Universality, I purposely put it with a small u. I don't know another word to use, but I'm going to talk a little bit about that. These are quite common. Something like this is quite common in a number of flows when you get near this limit point where the turbulence, where you make the inevitable return to laminar flow from turbulence. Okay, in parameter space. Okay, so let me go on. The three things that I want to discuss in my time is distinct types of states that one finds along here, and I'm going to go ahead and put this up here and keep it for reference. These are these numbers are more or less from experiment. So imagine that all right, let's just look at this. This is schematic. There's a laminar branch as a function of Reynolds number. There's a laminar branch, and then if you get up here in the turbulent states, what you see is there's uniform turbulence, that is, no pattern. I'll show you more pictures. You come down, there's a transition region, experimentally about 410, 400. You see these periodic states. Lorette only discussed in detail some periodic states. Then there's some localized states, and then one returns to laminar. So I will explain these, but I want to just that's what I'm going to discuss, the distinct types of states. I want to talk about an order parameter to characterize this transition, at least the transition from uniform turbulence to some sort of periodic state, a pattern state, and some connection to pipe flow, possibly. Again, the computational domains you've seen before, I won't spend time, well, let me just skip it. And again, you've seen this before, but maybe Srini can ask. So let me just say, this is, by the standards of what we do now, this is the very first simulation in which we saw the patterns appear. By the standards of what we do now, we vary the Reynolds number much, much more slowly, essentially adiabatic. But what's happening here is, again, I thought I would need this. I made this sketch. So what you're seeing here is we're making measurements like this. We're making measurements there. This is completely unprocessed data. It's along a line of points like this. It's just kinetic energy along those points, completely unprocessed. These are time series going upwards in time. We start at Reynolds number 500. If you were to look at it in space, it would be uniform turbulence. As I say, there's no structure here. You go up in time, you make the steps decreases in Reynolds number, and beyond some minimum Reynolds number, you see the formation of the pattern. Okay, and here, okay, don't worry about the size here. We were in a hurry. This was the first one we did 5 years ago. We were in a hurry to get some pattern. We now go for up to 40,000 time units at each Reynolds number, depending on what we're trying to study. That's a long time. And then, again, this is what, if you were to look at the state here, that's what it corresponds to, which is I've sketched here, just to make sure everybody's clear about that. All right, so now there's these distinct states. Now here's so this is 43,000 time units, about 3,000 or 4,000 or so at each Reynolds number. Again, uniform turbulence, decreasing Reynolds number, and you see these states. What I'm going to tell you, I'm now binned up. Before I was just showing you raw data, I've now colorized it. I just made pixels for the intensity of the turbulence. You can see here it's more or less uniform, and then you get this periodic pattern. There's a lot of details in there that I'm just going to skip. What I want to tell you is that there are distinct states here. How do we know they're distinct? Well, we could just see it with our eye, but then you can do some numerical experiments to try and verify this. What I'm going to do now is, again, time is going upwards. The Reynolds number is now fixed at 350, which is the main state that Lorette discussed. It's right here. So I've come down. I'm now going to fix the Reynolds number, and I'm just going to look at this state. And what I'm going to do, instead of varying the Reynolds number in time, I'm going to change the domain length. Okay, I'm going to start with a small one that only supports one little patch of turbulence, little meaning 40 or 50. And then I'm going to just grow the domain. And when I do that, what happens is, as the domain gets larger, that turbulence splits into 2, and then it splits into 3, and that just shows the final profile at the end. So the turbulence wants to, as long as I keep growing this, the turbulence will invade, and you will keep getting these arrays. So we call that periodic. If you do the same thing at a lower Reynolds number, 300, if I go down here and play the same game, I'm just going to start with something that's it's necessarily periodic because it's periodic boundary conditions here, but I just grow my geometry. This region of turbulence could care less about how big the geometry is. If you look at the tails of this, you find it exponential. It's exponentially localized. Okay, so there's a distinct transition here between these kind of periodic patterns and isolated ones, and the experimentalists knew this. The experimental papers, and we agree on the Reynolds number of the transition too. I think that's just a movie of the, you can't even see it very well, of the localized state. Let me skip it. Now, between the uniform case where you see turbulence everywhere, and this case here where you see more or less steady pattern, there's intermittency. All right? Now, this doesn't show it so well, but you can see there's a little patch of laminar flow there, a little patch, and they kind of come and go. This is a relatively short simulation. If you run on a smaller geometry, but big enough to hold one wavelength, and you run it for a long time, 40,000, it's cut off. This is 40,000 time units, convective time. You see that it just will never settle down. It just never settles down. Okay, and again, the experimentalists, they didn't use the word intermittency, but they also saw this in the transition between when you see the uniform turbulence and the, so there it is. Now I can, okay, we get good agreement. I'm just going to skip that part. So one of the things you'd like to do is, from the point of view of pattern formation or otherwise, is you'd like to characterize this transition. And it's harder than you might think. And let me just show you what, again, just remind you what the transition we're talking about. So these are back to raw time series. Fixed Reynolds number in this case, fixed Reynolds number 500, where I have the uniform turbulence. Again, you simulate this as long as you want. This is what you see. You go down to some kind of intermediate Reynolds number, about 400, and you see this, it becomes kind of laminar, quasi-laminar, in kind of this very irregular way. You go down to 300, and it's much, much more regular. And you want to quantify this, and particularly, I mean, the most basic question is, what is this point here? Where is the transition? Are there characteristic exponents you can associate to this, et cetera? So you need to find an order parameter. Now, I cannot explain, this is not hard, but I don't have time to explain it. So I'm just going to say it fast, and you can look at the pictures, and then if you're interested, you can ask me later. What we're going to use as the order parameter is the Fourier transform of this, or whatever, whether it's this or that, the Fourier transform at the wavelength corresponding to the pattern. Okay? That's what we're going to do. Let me just, no, maybe I won't even say that. So I take this state at 500. At each time instant, I Fourier transform it. I look at the longest wavelength mode. It's a complex number because there's a phase in addition to an amplitude. I plot it here, so I get a whole bunch of these. I'm then going to bin it up. It's rotationally symmetric, so I'll average over that, and I get this. And that's a PDF of this order parameter. That's span-wise velocity. It's what you call span-wise velocity. It's what everybody in this room calls span-wise velocity.
That's fine. And then the lines that are plotted are wiggling.
Yeah, that's a time. That's a measurement. That's raw data. You put a probe into your numerical simulation, and you measure span-wise velocity at that point, and that's and that's a graph of it.
That's many graphs going like
Yeah. For each, yeah.
series going.
Yeah. For each one of these. All right. So then you can see. That's why I say you can see with your eye that. So here's the PDF at 500. There's 400, there's 350, again, corresponding to this exact data. And you see something happening quite clearly. If you take cuts through these PDFs, again, of course, they're axisymmetric. I made them axisymmetric, even if it didn't want to be. I think it is, but I made them, so they have to be. These three cuts, I get, and you have to say what you're doing exactly, but these are definitely cuts through those, and this is what we have. This is the high Reynolds number case. This is a more or less transitional case, and this is the pattern case. And I'll just say, those who are used to thinking about phase transition, I'm not obsessed. I'm not trying to be a physicist and to map everything onto the Ising model, but it is useful to think in terms of you have a high temperature phase in which you have a free energy that has a single minimum. You lower the temperature, you go through a transition, you get these multiple minima, or in this case of axisymmetry, you get a ring of minima. Okay, that's standard picture. Free energy, you get a density that goes as minus exponential minus the free energy. That's what these look like. This one, by the way, is exactly Gaussian. Just to throw in some other Reynolds numbers, I'll have to get out of this. So again, in the uniform case, this case here, you see Gaussian centered at 0. What does 0 mean? The most probable value you see for the pattern wavelength is 0, the most probable value. As you decrease Reynolds number, what you see is you get a peak forming. The most probable value is away from 0, which means most probably you'll see some sort of pattern in there, but the probability of 0 is still finite, and then there's these periodic cases. I have to get off of this, don't I? Or how am I doing on time? I better get off of this. And then you could talk about the scaling, but that's a whole nother, all right, that's a mess. All right. So I don't know if you got anything out of that or not, but we do have an order parameter. It does seem to obey there are certain analogies with standard phase transitions, and we're still exploring them. Okay, universality. If you look, again, with the small u, I don't really mean to claim anything here is universal, but so this is plain Couette. Lorette also showed the Taylor-Couette experiment done by the same group in Sex A. And again, without going into the details of what you're seeing, basically you're seeing the same thing in a different experiment. If you look at, this is work of Cross and Legal. This is a rotor stator, so it's a flat bottom and a top rotating on top of it, another kind of shear flow. Here, dark is turbulent, non-dark is laminar. Those are all experiments. This is a simulation. Anyway, if you convert into appropriate length units, angles, Reynolds numbers, you see that all these are seen at approximately the same place. And it's always just before the flow relaminarizes, before in parameter space. So as you're coming down, again, for you guys, this graph extends way over there, but as you come down in parameter space in turbulence, and you start seeing these before you fall back down. It seems to be very common. So I'll say universal. And for at least a few years now, I've been going around saying that this seems a lot like puffs and pipe flow, and that there's probably a connection between these and puffs and pipe flow without anything more concrete. And so, given all the interest in pipe flow, we started doing some pipe flow simulations. This is work of my student, Dave Moxie. This is just a sketch. So we have pipes. We have two pipes. One, well, we can have any length we want, it's just a parameter. But we're looking at two, one of 50 diameters and one of 150. If you read the abstract, it says 400. We can do 400. I no longer think it's necessary. I think 150 will tell us everything we need to know. I'm just going to show you preliminary results. Again, it's the same idea. What you're going to be seeing are history data down the center of the pipe for different Reynolds numbers. Now let me go see what I'm going to show you. So again, this is high Reynolds number. So in each plot, Reynolds number is fixed. Time is going upwards. Unfortunately, there was a slight problem with the collection of the history point data, so we don't have the uniform cases on this. We have some of the data for statistics, but we don't have it for making these nice plots. Anyway, so we're at 2150, and you see this kind of intermittent behavior, big intermittent event here. And then finally at 2000, you see, looks like a nice regular behavior for at least for 2000 time units. If you were to look at just half, I don't know exactly what time this corresponds to, but if you would just look at a piece of this course, you would see what looks like a puff. I mean, that is a puff. Anybody would call that a puff. The PDFs, again, these are very preliminary. The PDFs show all the characteristics. I don't know if the exponents are the same or not. They show all the characteristics of the transition in plane co-ed flow. I mean, certainly qualitatively they're similar. Whether quantitatively they're similar, I don't know. And again, we're still running the 150 diameter pipe, but just to show you something that's come out of this, again, intermittent events. And the final thing, and I just threw this in at the end because I'm glad Lorette emphasized it. I can emphasize it again. Look, you're coming along. This is back to plane co-ed flow. This is a length of 90 gaps, 90 half gaps. And you're coming along with turbulence. And we see this kind of thing very, very frequently. Very frequent. If this were an anomalous case, it wouldn't be any point in showing it to you. But you see it, you get to a case where a large part of the domain collapses down to laminar flow, but not all of it. And that's all you need. And this, in order to have the turbulence intensity increases here, and it will just spread out. And so if you're looking at transition phenomena, the size of the domain really, really matters for this reason, if not for other reasons. Okay, and I want to thank the people who provided us with the computational resources. And I'd really like to thank the organizer. I think this has been a great workshop, and thank you for that.
Yeah, 15, 20 years ago, there was a lot of talk about turbulent spots in these types of flows. And the top would start to be a spot. Now the top seems to be a band. So, I mean, what's the relationship to turbulent spots?
Okay. Paul may have a different, there's people here more closely associated with the work. Unfortunately, there are people here more closely associated with the work. No, if I had to guess, I would say that that a lot of these spots are stripes, bands. That if you put it in a bigger, what do you think, Olivia? I mean, François, do you think? I think a lot of these spots, that if it didn't wasn't seeing the boundary, it would have grown into something more resembling a band. What do you think, Paul? Don't know. François says me. So that's what I think, maybe. I don't know.
But I mean, in plane co-ed flow, you can get a spot which doesn't grow into a band.
Yeah, but how large is it compared to the boundaries of the domain? That's the question.
Okay, you think that would spot in co-ed flow would
Well, if you plot a normal, what you're thinking of a spot on the Prigent show graph, it's very small. It's the size of a band.
Okay.
See, that's the difference. So if you have to put it in something that's 8 times bigger.
If you look at the length scale dependence in plane co-ed of the Reynolds number, it really looks like the transition is continuous, or at least that the jump is very small.
I think this is the second order. If you want to discuss this in terms of phase transition, I think it's second order. If that's the
Yes, but if you look at your graph, when you change the Reynolds number smoothly,
Yeah.
the peak is very close to 0. So you remember your histogram was splitting from something like that
Yeah.
into
Yes.
2 bands.
yes.
So can you comment on that?
I guess I don't understand. Okay, so
Can you go back to the
PDF?
PDF of in plane co-ed?
Should be about the next one. Let's skip it. Yes.
Yeah. If you look at the black data,
Yeah. Okay.
I mean it really. I mean, do you have any data close by in Reynolds number?
Okay,
In-
shouldn't it, this,
between
this,
the red
is,
one
okay,
and
this
the
is
black
not
one?
wavelength. This is a fixed wavelength. This is amplitude you're looking at.
Yeah, sure.
Okay.
Oh, all right. Yeah, okay.
This is amplitude. So the amplitude of the mode grows at a fixed wavelength.
Yes.
Yeah, that's what you'd expect. I mean, I think you agree.
So is the last question, perhaps.
In the pipe, are you in a co-moving frame there when you see the?
Yeah. Thank you for saying that. Of course, I'm going to come and it varies with Reynolds. Sorry. Thanks.
That explains it, right?
Yeah, of course. No, our puffs don't just sit there. Sorry. Right.
Thanks again. And